let's go ahead and get started. Want to quickly go through, again, what we'll be talking about today is strategies for very large data visualization. In particular, we're looking at 1 billion cells, and what we'll show you is that we can already view 1 billion cells in Tecplot 360 2012 R1, I believe, which is our most current release. So, quick agenda, and before we even get started at that point, it's probably a good idea to ask you about the largest grid you're running. So I'm going to go ahead and launch a poll. And so what you can do on your side is you'll notice that we have how big is the largest grid you've run in the last 12 months. And you can select anyone you want. I tried to break this up into bite-sized chunks, so to speak. So we're looking at over a billion, 400 million to a billion, 1 to 400 million, and less than 100 million. And for those sticklers out there, if you're 400 million in one cell, go ahead and put yourself in the 400 million. And I'll keep that poll open for just a minute here as we take a look. And it looks like a fair amount of people have already answered this. So we'll go ahead and let's go back here. And I'm going to go ahead and close that poll. We have about 75%, which is usually about what we try to do. And I'll go ahead and close the poll. And I'm going to share those results with you. So you can see that for the most part, a lot of people are looking at less than 100 million cells. We have just a few people who are looking at a billion cells, about 3%. And about 3%, 400 to a billion, about a third, 28% in the 100 to 400. Does that surprise you at all, Scott?
No. I think it takes a lot of computing resources to compute something over a billion cells, but no. So that's consistent with what I'd expect.
Okay. Yeah, it's kind of consistent with what I hear out on the road as well. So, all right, let's get back to it, and we'll go ahead and continue. Okay. So let's just take a quick look. If you haven't already done so, if you want to connect with us, we are on YouTube, Facebook, Twitter, and LinkedIn. Go ahead and take a look at the addresses here. You can just search Tecplot, and you'll get it pretty quickly. Okay. So for today's agenda, we're going to spend the morning session, or the first part of the session, really diving into some of the trends that we're seeing in the CFD analysis, computational hardware, and some of the implications that we see of this the current strategies that a lot of organizations are using around this. Then we'll talk about Tecplot strategy, Scott, and this is actually something I think that's pretty interesting in that we are doing something perhaps different than a lot of people, and we'll want to spend a little time on that as well.
Right. Yeah.
We'll also show you kind of the performance of 360 improvements over time, and really try to relate that to other offerings that are out on the market so you can at least see kind of where we stack up. And the last thing we're going to show you is a virtual desktop environment where we're actually going to use VMware, and we're going to show you a virtualized PC that's running at our colo, which is our co-location where we keep our data and also store our website and things like that. We're going to show you how you can do that and some of the implications. I mean, it's really fast and it's kind of an interesting approach.
Right. It uses a new technology, well, reasonably new, PC over IP, that really reduces the latency and makes it a lot faster for the high latency connections like you get over the internet, for instance. So
right.
This could be an excellent solution for those folks who are running cases at a remote site and would like to visualize it using Tecplot.
Right. So and to that end, before we get started, we're going to do one last thing, which is, we have a number of polls that we'll ask along the way. But one thing that we'd like to get a sense of, one of the things we're running into, is just what people have at their disposal. So here's an example where we're asking about how much RAM you have in your local machine. And for example, in my machine I have a little over 8 gigs, so I would be in the 16 or less gigabytes. And again, for those sticklers, if you have, well, I guess you really can't have more than 16 gigabytes. Yeah, 17. Or those lucky people who has like 18 gigs. We're really looking for if you're in that range. So over 60, 64, 32 to 64, 16 to 32, or 16 or less. So if you go ahead and just quickly populate that poll, and we're at about 75%, 77%. Okay, we're going to go ahead and close that. and let me share with you those results. So, again, I'm surprised here that 50% of you have less than 16 gigs of RAM. Wow.
Yeah, that's a little surprising to me too. Of course, maybe we're dealing with mainly laptops, which typically have less memory. But we're seeing a fairly high percentage of our customers now have fairly powerful desktop machines.
Yeah.
Yeah, interesting.
Well, the people who have 64, which is 5% of you, hey, that's great. I know that I'd certainly, that's what I'd like. And as I'll show you our Colo, we have about 48. So, okay. So with that, let's get into the meat of our discussion. And Scott, I'll kind of turn this over to you. And we'll talk about the impact of low computational resources, or low-cost computational resources.
Yeah, well, the real trend over the last, since the microprocessor was first developed, is the continuing increase in performance, the exponential increase in performance. Everyone knows about Moore's law, both the density of the transistors on the chip and effectively the performance and the memory are doubling every 18 months or so. As a result, you get we now have an enormous computing capability, and people can run very large cases. Doesn't mean as we saw in the poll, not everybody is running 1 billion cells, but there are a lot of organizations that have done that at least occasionally. And so the net result is you were getting and we'll talk more about this, but we're getting a general increase in the number of cells that people are running on their CFD cases. And so if we just hit this. Now there's another trend as well, and that is not only are they able to run larger cases, but in many times, instead of running larger cases, they're actually running a lot of cases that have a smaller grid, so that you can distribute your computing resources one way or the other, and this chart sort of shows that.
And that's certainly something that we're seeing more and more of. In fact, recently we were dealing with a company you wouldn't really be thinking of doing lots of cases, but in fact this is a manufacturing company that does nozzle design, and this is a spray nozzle for coatings. I mean, this is manufacturing at the heart of manufacturing, and they're running 50 to 100 different variants of different nozzle types for different types of coatings. Right. And it's amazing the number of data files that they're looking at, and each one is highly resolved. I mean, we're talking about 100 million cells. And a lot of times they'll actually look at, it's an unsteady solution, they'll look at, 10 to 100 solution time steps. And we're talking terabytes of data. It's just, it's mind-boggling how quickly this has been changing.
Yeah. So if you want to visualize 1 billion cells, you need to really look at the architecture you're using. So you want to project how the competing options will perform over the next few years. There's a famous quote from Wayne Gretzky that he skated to where the puck would be, whereas everyone else skated to where the puck was. And we're trying to skate to where the puck will be over the next few years, so our architecture, as we modify it and improve it, will be optimized for the future configurations, computing configurations. So as part of this, we're really focusing on bandwidth. Latency is the second component that you have to deal with, but latency is not going to be considered generally here. So in general, just a quick look at the pipeline, the visualization pipeline along the bottom here. First you have to load the data, and then you do some sort of feature extraction. It may be an isosurface, it may be a stream trace, or it may be a more complicated feature like a vortex core, and then you render it, and that goes to the display.
And recently there's been so much talk about the cloud, and specifically I know yesterday, I'm sure everyone got theirs as well, but Google gave us our Google Drive, or whatever they're calling their variant of their hard drive in the cloud. Do you see data on these large computational resources actually being more cloud-like, and so latency becomes even more of an issue and how it will load, but it may seem local. Your computer may think it's local, but it's actually on the cloud somewhere?
Well, I think that's certainly possible. We haven't seen a whole lot of that yet for various reasons. I mean, there are a couple of organizations that are using cloud-based computing and storing their data on the cloud. But yeah, latency and I mean, even in that case, I think the primary issue is probably bandwidth. The latency really comes in when you have remote rendering. So if you look at the pipeline, if everything to the left of the display is out on the cloud, well, then you need to start thinking about latency in terms of the response of say to mouse movements if you want to do view changes. That's when you really notice that. And when we talk about our the VMware solution, the remote display solution, we'll talk a little more about that because it does a good job of helping you when you have latency issues.
Yeah, I think we can thank Netflix and other streaming media for really kind of handling the bandwidth problem, because if you look at it, that's what most people are doing nowadays. Who watches anything live anymore? Who has time for that?
That's right.
Okay. Well, let's continue the discussion by talking about how data sets have been growing, and really, there's this question of, well, how much grid is enough?
Well, yeah, and of course it depends on what you're doing. We're looking at large grids today, so we're talking about complex configurations. Maybe you can imagine having a full 747 and you're trying to visualize it in a landing configuration, for instance. So it's a very complicated configuration, high Reynolds number. Now, if you look at this table on the bottom, we sort of charted out, well, how large is the grid really need to be grid resolved for that type of configuration? Of course, it depends on the type of fidelity you have. If you're looking at Euler, an inviscid calculation, maybe 10 million cells would be enough. If Reynolds average, Navier-Stokes are saying it's in the 100 million range, or actually that's more of a billion I put in there. Excuse me. And large eddy simulation, maybe significantly finer grids are required because you're actually trying to resolve these vortices that are being shed in the wake of the aircraft. A rough estimate would be in the 10 to the 14th cells, and if you're trying to do a direct numerical simulation, you really need to get your grid spacing down to a Kolmogorov scale, which is the smallest scale at which turbulence is really, all turbulence is gone at that scale. It's all laminar. And so, that a rough estimate, that comes out to about 10 to the 20th cells. So if you look at that, people are going to go to these higher fidelity methods as they're available and the computing resources can handle them. So the net effect is we're predicting that you're unlikely to ever have enough grid to really get all of the details of the flow field. And so just say that the largest cases you're likely to run is going to continue to grow exponentially, grow with Moore's law, with the capability of the computing resources.
Yeah, and that's, again, very consistent with what we see, although, again, the audience looks like, for the most part, is looking at, 100 million cells. And I think that's likely a function of their computational resources more than anything.
Well, not everybody has the huge clusters, and so, but then I imagine those folks, 10 years ago were not running 100 million cells. They were probably running 10 million or less. And so, everybody is growing. It's just a matter of where you are on the spectrum.
Yeah, and then that spectrum is, as you can see, quite wide in terms of what people are doing. So large is always what's large to you.
Right.
So in that context, we should quickly discuss, how does that play into
So what we're doing, what we're doing now is we're looking at each of those components we talked about in the pipeline. And the first component, if you're again skating towards where the puck is going to be, the first component is to look at how you project that the hard disk performance is going to vary over time. And there is a Moore's law type of law for this. It's called Kreider's law. It says that this is for size of the hard disk, capacity of the hard disk. It doubles annually, so it's actually growing faster than Moore's law. You know, the amount of data you can store on the disk is growing very rapidly. On the other hand, the transfer rate for getting data off the disk is only doubling every 3.5 to 4 years. It's growing much more slowly. The net effect is, you know, we now have disks that it takes us 5 hours to copy, you know, because that's reading at full speed, and that's going to continue to get, you know, the difference between the two is going to continue to broaden. Now, there are ways of improving your time to read, your sustained rate using parallel disk farms and parallel data storage systems, and basically striping your data across multiple disks. But that is not likely to keep up with the fact that the capacity is growing so much faster than the data rates. You know, if you think about it, the highest end computing centers will probably increase the spindles rapidly, because they're going to have to increase the number of disks every year to keep up with the growth rate of the data sets. So the highest end compute centers may do that, but the majority of people, you're just not going to be able to justify the fact that you're increasing the number of disks exponentially every year. So that's so essentially what we're saying is time to read from the hard disk is projected to increase. This is for the typical data set now. It's projected to increase along that line you see there at an exponential rate.
And we also see a trend towards a lot of organizations who, you know, they have strict data policies that you can't even keep your data around. So you may actually have your data, it's this very large file, but not only is reading it off the disk, hey, getting rid of it off the disk can be a slow operation. And so, you know, a lot of organizations are struggling with, where do I put this information? How do I get access to it once I've put it somewhere? Do I rerun it? And so this is a much more inclusive problem than just even reading it off the disk. It's, you know, how do you store it? Where do you store it? And what do you store?
Right, exactly. And that, of course, that's a topic for another day, but there's a huge issue with how do you compress this data to where you can actually access it, or do you not, or do you just rerun it, which is, if you think about it, a form of extreme compression.
Yeah. So, yeah. Well, in that context, let's talk about the bandwidth as well, and then we have a couple more poll questions we want to interject here, but maybe we'll do that right after this.
So the bandwidth is the second component of that data pipeline, the visualization pipeline. So you're reading the data, and it has to go through some sort of network, because typically you're not reading off of a local hard disk. Usually, at the very least, you have some sort of storage area network you're reading off of, or maybe it's one of these parallel file systems. And then so you have to access this over either your local area network or a wide area network, or in the extreme case, over the conventional consumer internet. So basically, the LAN and WAN bandwidth has been doubling every 2 years. Mm-hmm. So it's not growing quite as fast as Moore's law, but it's definitely growing faster than the sustained rate for getting data off the disk. Mm-hmm. By the way, going back to that, the sustained rate means if these files are really large, so they're going to overwhelm any disk cache that you have. It's not like a database where you can take advantage of a disk cache to really increase your I/O. Mm-hmm. In this case, it comes down to you're really pulling data off the physical disk, not off of some cache. Mm-hmm. All right. Another thing that happens is that, and these are less important perhaps for our discussion today, but the truth is the number of cores on the computer is pretty much doubling every 2 years as well.
Mm-hmm. And that's kind of an interesting thing too. You think about the cores, and certainly the new i7 that's going to be coming out from Intel. Yeah. And of course, the way that they're calculating cores is getting kind of funny in that context. But they also talk about the fact that it's not even you can't just throw more cores at it, which is kind of the American way, right? Well, I got a big problem, throw more stuff at it, more resources, and when we were out at NASA Ames very recently, they were talking about, to keep NAS running, they may need to build a nuclear power plant next to NAS.
Yeah.
So it's power intensive, and so having a lot of cores, although great, you got to be efficient in how you use them.
You do. There's some recent, 2007 they had a study where they estimated that the power usage by just the computers in businesses and compute centers, et cetera, used 5% of the electricity in the United States.
Wow.
And that's been growing.
Wow.
So yeah, this is not just keeping the cost down by keeping the amount of computing power you use low. It's really about environmental aspects, and just really keeping energy usage in our country as a whole to a reasonable level.
Mm-hmm.
So, yeah.
Well, in that context, we're asking the question: how many cores do you have on your local machine?
Mm-hmm.
And for example, my machine, I have 4 on my laptop, but then my colo has 8, so I would put myself kind of in the 8 to 16 range. So we're curious, what are you running? What typically are you looking at 16 or more cores, which would be pretty cool. Not many people have that, but some of you do. And we'll leave that open for just a second, and looks like we have 78%. I'll go ahead and close that poll and just share the results with you very quickly. So a couple of things to point out. It looks like more than 16, which is a significant number. About 12% of you have quite a few processors locally. 40% nominally are between 8 and 16 cores, and then say the bottom 50% were more or less 7.9 or less. So that again, not uncommon with what we see out in the real world, but not as many as maybe some people projected. Everyone would have 100 cores on their desktop by the end of this year, and I'm not sure that's going to happen either. But I guess we'll
maybe if Knight's Corner comes out, we'll see that.
I'm looking forward to that. Okay, well, let me go back then, and we can talk about this in the context of performance. So we talked about visualization software. You talked about the pipeline. Now, based on all the information that we've shared up to this point, what were some of the conclusions that you drew and that we're using to guide our development efforts?
Oh yeah, so just pull together what we've said before. You look at, and just looking primarily at the hard disk read transfer rates and the network bandwidths. You can look at that chart on the right, and you can see the red line is the hard disk read transfer rate, and the green line is the LAN bandwidth, and the blue line is the wide area network bandwidth, and time to actually transfer the data sets that we project over time. And don't get too hung up on the fact that I've done these as very narrow lines. The truth is there's a lot of variability over, with different organizations and different systems. But the trends are going to be along this line, and that is, you can see that if you that the hard disk read transfer rate is going to dominate at some point in the future, if it isn't already.
Mm-hmm. Yeah, and that is, I think, a certain natural consequence of kind of where people are going with this. So.
Right, and there's two aspects of that. Not only is it going to dominate, which means you need to solve the problem of reading the data off the disk. Mm-hmm. You can't just use a feature server which remotely reads all the data off the disk and then sends features over, because you're going to still spend all your time reading data off the disk. So you have to address the problem of reading data off the disk. And the second aspect is, if you don't address that problem, you see that the performance of the visualization software is going to get worse over time. Mm-hmm. And it's going to get worse over time regardless of whether you're using a client-server system or whatever. It doesn't matter. It's going to get worse over time. And so this is something that you need to focus on.
It's something that certainly we identified as if this trend turns out to be true. In fact, there's no breakthrough technology that really changes this. We've got some real bottlenecks coming up, real constraints that really are going to impact the ability of people to get work done.
Yeah, and there may be breakthrough technology. If everyone went to solid state disks tomorrow, then it wouldn't be a problem. Now, I suspect that even if that happens, most of our customers are still going to have the normal hard disk. So this issue is going to be around for a long time. But I don't suspect that there's going to be any major breakthroughs for the next 5 years at least.
And we'll look. So based on that, I mean, really, there's a couple of things that we identified, and really, they're driving our strategy. So perhaps, Scott, let's talk about, since that is the problem, how are we addressing
that? Sure. As we said, you have to read less data. We've already talked about the problem, I think, enough, but you have to read less data. And so the basic approach is a lazy loading approach. You only read the data you need. And we started doing this, I think it was about 8 years ago when we, with the first Tecplot 360, we started transitioning to a load-on-demand approach, where you only read the data you need at a variable and zone level, and that led to substantial improvements in performance. In fact, Tecplot 360, today's Tecplot 360 is an order of magnitude faster than Tecplot 10 was, at least. And if you're looking at an unsteady case, I mean, it could be 2 orders of magnitude or 3 orders of magnitude faster, depending on how many time steps you have. Right. So it's a huge difference. That we've had some huge improvements in performance over the last decade. And so if you haven't tried Tecplot for large data since, the 1990s, now's the time, because it's a totally different product than it was.
And that's actually something to point out, that we go around the country and we talk to a lot of people who are doing this type of work, and they'll say, gosh, I'm struggling with performance, and then we'll ask them, well, tell me about, what are you using computationally? Well, I've got it's on my laptop, I've got 2 cores, and I'm on Windows NT. I'm like, wow.
And I'm running Tecplot 10.
I'm running Tecplot 10. And it's frustrating because we have done a fair amount of work there. So I'd encourage you, if you have access, and most of you, if you have support, you can just download the upgrade, and I'd encourage you to go ahead and do that as soon as you can. You're going to really see some benefits. And actually, it's probably worth showing just how much of a benefit. So we talk about this multi-core strategy, but one of the things we talked about, and I alluded to a little bit, 5% of our total power consumption is actually being used for these high power computing centers.
Right.
And that's interesting. And so, that as a good citizen, one of the things that we're trying to do is figure out how do we be more efficient, because using all those cores is great if you use them all. And maybe, Scott, you can talk about that a little bit.
Tecplot uses multi-threading. Some people think we aren't parallel because they look at Task Manager, and Task Manager shows it only using 1 core most of the time.
Well, on Linux, it's a little different, right? It's
top or Task Manager, but the truth is, it is multi-core. It uses the cores, and it uses them pretty efficiently. To see this, you only have to try running Tecplot, doing stream traces, and do it with. There's an option to turn the number of cores you use in the configuration file. You can turn the number of cores you use to 1, and try and compare it. And you'll see it scales pretty well with the number of cores. So, but the thing is, in Tecplot, the threads are only active when they're needed. So you're not going to see it most of the time on a Task Manager or a top. So it's only when it needs to be used, and that is a very efficient use of the computing facilities, as opposed to some MPI-based parallel visualization codes, for instance. They pretty much lock up the cores. Now, the operating system will tear them away to swap in other applications if necessary, but they sit there and spin. And so if you look at one of those and you look at Top or Task Manager, you'll see all of the cores being used even when nothing's happening. and that's not an efficient use of the cores. And so the benefits, more resources are available to other applications. If you're doing a large case in Tecplot, you can be running your other applications as well, and it'll work pretty well. Less memory usage, lower power usage. That goes back to our environmental concerns, and you can run larger problems on smaller computers, and these are all because we're using the resources efficiently, the compute resources efficiently.
So in the context of computational resources, one thing that we're always curious about is the type of simulation people are doing, because of course, sometimes if they're doing, Euler methods versus full Navier-Stokes, they're going to be using more or less computational resources, may be able to get, they may be doing more cases. So in that context, we're curious, and we'd like to know, when you think about your primary, and now we're not talking about every computational method you use, because in fact we'd have to have 100 checkboxes, but if you think through what are the key or the most prevalent type of simulation you run, is it primarily Reynolds average, Navier-Stokes, Euler, LES, direct numerical simulation, or are other types of simulation and or test data? I guess you can, if you're unsure, you can put it in other. And we'll let this go real quick. We don't want to, we'd like to be able to get this data. We have about 65, almost 70% of the people who have chimed in. I'll give it about another 10 seconds here. So if you want to add the type of work you're doing, go right ahead. And it looks like we're just over 75%. So at this point, we'll go ahead and close the poll, and I'll quickly publish that for you. So one of the key things you see here is that what was interesting to me by looking at this is over 50% are just doing full Navier-Stokes CFD, and then other. Well, that's always the challenge with other is who knows what other is, but it could be test. So it's interesting to put that in context for a moment, that a lot of people that we're talking to are doing Navier-Stokes CFD calculations, and they are computationally intensive.
Mm-hmm.
I mean, these are not cheap to do. Okay, let me hide that, and we'll continue our discussion. Okay. So let's talk about the overall performance improvements, and this is, we only took a snapshot, and this is an ongoing process, but maybe we can talk about just what we got done, for example, in one release, which is 2009 R1, which was our first investment in large data.
Yeah, we took, starting in 2009, we had a thrust where we said, in 3 years, we're going to do 1 billion cells. This is 3 years, right? And so we had a sustained effort since then. And as a result of that effort, some operations have just improved dramatically, including some of the loading operations, especially for finite element data. Mm-hmm. And so you can see this chart on the right, and this shows that over just this one period, we increased our performance by about a factor of 3.5. Mm-hmm. And this is just doing a series of small improvements and adding multi-threading in various places, and staging in the loading process, and just a lot of things to improve the performance, and that has continued. And it was ongoing at a lower level before, and it's continued since, and our performance, as I mentioned before, has improved by at least an order of magnitude over Tecplot 10 when we first started this effort, when we went to Tecplot 360. And so we mentioned, we did data loading, slicing, and isosurfaces. These things are parallel. Mm-hmm. Stream traces are highly parallelized, and we did a lot of work to improve the rendering speed as well.
Yeah, so it's been a sustained effort, and it continues. We also do some benchmarking versus other tools on the market, just to understand kind of how do we fit in to the ecosystem in terms of overall speed. And we really look at kind of 4 main areas, the areas we just talked about: stream traces, slicing, isosurfaces, time to first image, which is it's a funny one to compare. It really depends on what that first image is. Yeah. If the image is a box that shows the flow domain, your far field edge, well, that's different versus if bringing in the full model and actually showing something.
Right. Or if you just load a geometry, right, and you're just seeing the geometry. Those things that's not how Tecplot works. Tecplot you get a you're getting the fluid data available to visualize right away, and so that's why we talk about the difference between Tecplot defaults and their defaults, this particular application we're comparing against. And you can see, just in general, if you look at this bar chart, Tecplot, regardless of the defaults, as long as they're consistent, Tecplot is faster for most of these things than this other application is, and a little slower or comparable for the time to first image. But as we mentioned, our first image is a little more complicated than most folks. And so this idea that Tecplot is a whole lot slower than our competition doesn't bear any fruit. It doesn't seem to be true. Now, this is just one example, but we have some customers that we've challenged to do the comparison. Just side by side, compare Tecplot to the competition, and apples to apples. So they're both running on a local machine, say, and in most cases they've been pleasantly surprised by Tecplot. It's not saying it's always faster than the competition at this point, but it does pretty well, and it's often faster than the competition. So if you we challenge you guys to try that too if you'd like.
Yeah,
let us know. Let us know.
And it's also important to point out, we talked a little bit about this offline before we got started here this morning, that when you think about these very large simulations, and you talk about what do you actually present, and I went back and I was looking at most of the papers that were around CFD that were published in Nashville, and I looked at what was actually published. Well, you have lots of equations and a few XY line plots, oftentimes made with Tecplot. And these actually do come from the simulation data, but it's unlikely that you're going to see very colorful image. You have a few. Obviously, you want to have some in there. And certainly for a report or a group meeting, actually showing the full volume data is useful. But where the rubber meets the road, it's often the engineering plotting, which is one of the unique things that we've focused on over the years, is making sure that not only can we provide a vehicle for the interrogation of the volume, but at the same time, we provide the tools for engineering analysis so that you can take those colorful fluid dynamics, which is sometimes called that way, and really pull out the quantitative data that you can present and say, well, here's how it compares to test, for example, and that's why we have high confidence, and then we verified that this case actually verified the code gives the right answer, and then validated it against some tests, and that's really, at the end of the day, what we're trying to do here. It's not to show a picture of vortex shedding per se, although that can be helpful as well.
Yeah. So you can't focus just on the big data 3D visualization. Yeah. In the end, there's this cascade of information down to these engineering plots, and that's where decisions are typically made. It's on the engineering plots.
So then here's where the rubber meets the road. I guess we talked about this briefly, but maybe people would be surprised to know that on a daily basis we run a 1.2 billion cell model to get timing.
Yeah, the only way to be sure that your performance is improving is to test your performance constantly. And that's what we do. We run this case constantly. And as we're developing on the latest version, in internal builds, and you can, we want to make sure that we don't mess things up. And so this 1.2 billion cell case, it's tetrahedrals, and at this point, it takes about 5 minutes to load the data, and it really only takes seconds to generate an isosurface, for instance, or a stream trace. And the view changing on this particular computer, I should mention, this is a reasonably powerful computer. It's pretty powerful actually. It has 96 gigabytes and 8 cores. It doesn't need 96 gigabytes to do this. We can do the 1.2 billion cells probably with 64 gigabytes, but if you're at 48, it's going to be swapping a lot. So it does at this point require a fair amount of memory, but you can do it. It runs and it actually performs quite well once you have the data in.
And we run a lot of tests. We only put in one test here for stream traces, but I believe in this case it's generating 1,200 stream traces.
Yeah, this is a lot of stream traces. And so, and you need that to actually be able to measure anything, because our stream traces are really quite fast right now.
Yeah, and we're going to actually show you an example here in just a minute. We're going to actually demonstrate this PC over IP technology, and we're going to go out to our co-location, and we're going to run some stream traces just to show you what that looks like. Okay. We'll see how that works. Huh? So in that context, maybe we ought to talk about that a little bit.
Sure. One of the things we've been looking at is, everyone knows we don't have a client-server application. But the truth is, other companies have been working on client-server for us for some time now. Yeah. And one of them is VMware. They have this virtual display interface. It's a virtual desktop, and it works so much better than X remote display. And really in a very real sense, this is a remote rendering. Mm-hmm. It's just that it's being done by a third party. So we tested it it's a hardware-based virtual desktop, so it is taking advantage of graphics hardware on the remote machine, and the performance, frankly, is great. Mm-hmm. And you can see on the right, this is just a chart of our tests. Now, this is the number of triangles. This is not the number of well, it has both the number of triangles and the number of pixels you can see there. And so this is a measure of the frame rate. So this is the interactive. How well does it rotate? Mm-hmm. And you can see for the most part, over most of that range, this thing rotates at faster, well under a second. Well under a second.
And so just to give you some sense of that, we're going to quickly see if we can disconnect this. We're going to walk over and we're going to bring up that virtualized environment. And you can see this is actually, I was telling Scott, this is the paradox. We're actually running virtually and then virtually again. So
looking in the mirrors.
Yeah,
right?
We're looking in the mirrors. So we're actually looking at streaming, as you can see. And actually, that's probably a good thing. So let's actually pop in here, and rather than have the stream over stream over stream, which I think it might actually cause GoToMeeting to go into some kind of quantum problem.
Quantum singularity.
Yeah, there's definitely. We're going to pop over to the environment, and we're going to make them the presenter. And so I'm going to show the screen here, and I'll also, for the sake of simplicity, I'm just going to change it over. So what you're looking at now is actually the desktop that we're running virtually, and this is the PC over IP technology. And we're looking at a simple case in Tecplot 360 2012 R1. And I wanted to show you a couple of things. First, just to take a look at this is what a lot of people do when we're out on site. They go, hey, let me show you my task manager, because clearly, you guys aren't using all the processors I have. So we'll do some things quickly, and we'll perhaps make this a little smaller. I have a large desktop here, so maybe we can see both of these simultaneously. Okay, so we're going to rotate this around, and you can see that, of course, you would want to see GPUs in this case more than CPUs, but, there isn't really any spike. And what we want to do is generate a series of stream traces. So we're going to generate a slice in Tecplot 360. And a couple of things, we're going to have a webinar where we talk about this in great detail, but we have added some additional features to Tecplot 360 2012. And in particular, what we're interested in is giving the ability to constrain a slice. And so what I'm doing here is just constraining the slice around my vehicle. And we'll kind of make this a little bigger. Okay, so really, if you only want to look at a slice in this area, one can do that. And then we want to generate some stream traces, but we want to generate those stream traces just from this slice, and we're going to generate a lot of them to see the performance. Now, thing to point out, this is running virtually. You can see I have nominally 48 gigabytes of RAM, and we also have, I think, it's at 8 processors, so just to give you an idea of what I'm looking at. And we're going to just grab an active zone or selected object. So in this case, I'm going to select that slice, and we're going to generate 1,200 stream traces, and we'll hit create. And what it's going to do is generate those based on the slice. Now, one of the things you can see here, hopefully it's not, okay, it's done already, dang it.
But you can see that it's used all of those CPUs.
Yeah, so the CPUs are all getting used. But then as soon as it's done, you can see that it lets go of them. So the processors are now available for other things. So if I wanted to pop into whatever this is, I guess I'm looking at Tecplot course, it's not important. But it's important to point out that here are some things that we've done to really, you can see, leverage or use the resources efficiently.
Yep.
So this, just to go back to it quickly then, to talk about rendering for a moment. So you can see that, we're looking at frame rates that are pretty reasonable. And again, we're doing this virtually twice, I guess. So you're getting this virtualized out to you being then streaming to you via Citrix. So, but it's worth pointing out that it can be done very efficiently. And what's great about this is that because the data is actually out at the data center, loading the data is pretty fast because they have some very fast disks out there, which is great. So this is how you can actually use PC over IP technology to address this concept of client server, because in principle this is running out there on the server. So
it's running out there on the server, it's rendering out there on the server, and it's displaying locally. And you have very nice interactive view changes. So
okay.
It's a good solution.
And we're going to go ahead now and go back to, we're in that the quantum loop. Minimize that momentarily.
Yeah.
And let's go to a sneak peek of some of the technology we're working on. And we'll kind of turn that back over to you, Scott. So I know that we've been working on some technologies, but maybe you can give us a sneak peek of some of the work that you've been doing.
Oh, sure. We have a research group in the company, and we've been focusing for some time now on the large data issue, and we have a solution that we're working towards now, where we have some very preliminary results, but the real goal, as we mentioned earlier, is to minimize the amount of data that you read, and the results we're getting are I believe, pretty impressive. It's faster, much faster. It uses much less memory. And this is key. The data loading scales with n to the 2/3, where n is the total number of cells, or points, actually. They usually are proportional. And so it scales with n to the 2/3. And that takes that curve that we saw before, where the performance of the visualization gets worse over time, and it turns it around, and the performance of the visualization will get better over time. So if we can do this, and we've already, we've got some preliminary results, we're going to fix the problem, the large data problem. So we have some preliminary results for a 1 billion cell grid, and for that case, the slicing and ISO surfaces, they load 2 orders of magnitude faster.
Wow.
So, and it uses 2 orders of magnitude less data. This is substantially, and this less memory.
Wow.
All right, so you can, if you took 48 gigabytes before, now you can do it in 2. It's a huge difference. And the stream traces, it's even more dramatic. Now this is for one stream trace, so if you have a bunch of them, it may not be quite as dramatic, but you get the idea. We load less data, and it's much faster, and it uses much less computing resources. And that's as much as I want to say about that right now. This is very preliminary. Just stay tuned, and we'll be showing some more stuff on this in the not too distant future.
Yeah, our goal is to actually have something for testing for those people looking at very large data, perhaps as early as the end of the year.
Yeah.
Perhaps. I mean, it depends on a couple of things. As always, software development is not a science. I know we have estimates that we think it's going to take X, Y, Z number of hours to code something up, may take longer. But at this point, all indicators are pretty good that we should have something to prototype and show people by the end of the year.
Yeah, that's the plan. And this is not just software development. This is research, so it's even more risky. But so far it's been wonderful.
Okay. So with that, again, we're going to go into the conclusions, and then we want to make sure that we have time. We do have some time for Q&A. So real quick, 2 ways to ask a question. One is if you have access to a phone and you have a microphone. Some people are listening on the computer and don't have a microphone. But if you do, you can raise your hand, and we can unmute you. You can ask a question. We can have a discussion about it. We have a small enough audience that will likely work. On the other hand, if you don't want to chime in that way, you can just type in your question in the questions dialog as part of your GoToWebinar dashboard. You'll see there's an area where you can input questions. So either one will work. With that, let's just kind of draw some conclusions to the discussion thus far.
Okay, well, as we've said all along, we're continuing to improve Tecplot 360 performance, and there's been a lot of improvement. Now, most people tend to make first impressions are strong, and a lot of people who started using Tecplot more than a decade ago, and frankly, it wasn't that fast then for large data. Mm-hmm. But things have changed. It's an order of magnitude faster than a decade ago, Tecplot 10, and I would say if you are doing large data and you're using one of the older versions of Tecplot, even one of the older 360s, mm-hmm. You need to upgrade because it really is much, much faster. And it's comparable or faster than most other tools on the market. Apples to apples, in the same configuration. And it's also more efficient in its use of computing resources than most of the other tools on the market. Mm. And so,
upgrade if you
upgrade.
Okay. We have a couple of questions. Let's start with Yoram. You have a question? I'll go ahead and unmute you. Yoram, you're on. Do you have a question for us? I guess I'm not hearing you.
Is he at the mute all? Do you need to unmute?
Well, I don't know if it works that way. I think I'm unmuted. Yoram. Okay. Oh, I do not have a phone. Okay.
So, yeah.
Sorry, he doesn't have a phone, so he can't really ask a question.
So just type in the question then.
Yeah, that'd be the easiest way. Couple of things. One person had asked about when you're doing rotation, does it recalculate stream traces? Because we had pretty nice refresh rate. If you're doing surface stream traces, there's this offset default that sometimes people have on, which sometimes will look like the stream traces or the contour levels are jumping off the geometry. It's just a setting, and we can actually show you offline how to do that, but that's usually an artifact there. So
it actually does not recompute the stream traces.
Yeah, it does not.
But that is just where, to keep the stream traces from going through the geometry, sometimes it offsets a little bit. Mm-hmm. And so it just that's actually a very simple offset, and it's using the computed stream trace. So no, the answer is no, it doesn't recompute the stream traces.
There was a question about the core usage on the PC over IP demo, which was on the computer. Is the data local? Well, it's a NSF mounted disk, but it's not actually local. So the answer to your question is that at that particular case, I think it's in the same data facility, but it's not like on the computer necessarily.
Is it or was it on the disk that was here? We might have one of those odd things where we're going out to a remote computer and reading data from our local site.
Yeah, we're doing it in reverse. Oops. Oh. Uh-oh.
Uh-oh. Yeah.
It seems like audio will not be recorded during that time. Is the audio back? Connecting to your audio. Uh-oh. That's a pain in the butt. Uh-oh. Uh-oh.
All right.
Uh-oh.
Your audio is stopped completely. So if you can hear us.
Okay. Sorry about that. Looks like the GoToWebinar service lost our audio, so I apologize.
You're back. Good. Thank you.
Okay, we're back.
Linda.
Thank you. Or should be back. Golly, that's so weird. Tim, thanks, Tim. That's twice you caught that. It's the strangest thing. Okay, let's see. Data on demand is nice, but when you have overflow solutions, you need to have all the data all the time. There's no free lunch. You want to kind of talk to that one. I'm not sure if I'm...
Well, that's an interesting, I mean, I'm not sure why you're saying that, because I mean you don't use all the data. For instance, for a time dependent case, I mean you don't need more than one time step at a time, generally speaking. And yes, for overflow, if you are doing if you're computing all your non-conservative variables from your conservative variables, this is a plot3D format thing typically, which overflow is essentially a plot3D format, then you do need to load more data. But there are techniques that we're working on that allow you to load less data than the full amount. And so, it's true certain file formats require you load more data than other file formats, but I don't think there's any format that requires you to load all the data.
Another question had to do with memory usage by Tecplot. There's two things on that. One of the things that I'd say is that people often will look at the task manager and they'll say, okay, Tecplot 360 is using this much RAM. But if you go into help about Tecplot, it'll actually show you how much it's actually using. And it's probably a good thing to look at. Depending on the size of your model, again, we get into that data I/O when we do load on demand. If you start to run into limitations on your memory side, we'll start to unload data as necessary. So, it's a complex problem. Someone had asked about, how do I increase it? Well, it's perhaps a complex problem, I guess.
Yeah, there are different options in terms of how it loads and unloads, how it makes the decision, and yeah, clearly, if you're for the particular case you're running, if it requires more memory than you have on the computer, it's not going to work. But most cases it doesn't require more memory than you have on the computer, and you can, it will offload the data. Now, I'm not sure. I'm trying to read the rest of the questions, but
there's a lot to that, and let's see. There's two things I wanted to. There was a question about when you load data, it has an option to load the first zone, and oftentimes that first zone is the biggest, and so and actually that's for you, Andy. One thing to point out is that even when it says load the first zone, so to speak, it may be faster, because oftentimes we're going to come up with either if it's a surface zone, if it's a volume zone, you're going to get the classic edge plot, which is nothing in it. So it shouldn't be that much slower, frankly. But that's a good suggestion to be able to select what zone you wanted to load first instead of just the first zone.
Yeah, our goal over time has been to make it so you don't have to do that. I mean, that was the approach years ago where we forced basically the user to limit the amount of, if they had limited memory and large data, to limit the amount of data they load. And in some cases that you'd still get a benefit from that, but not always. My understanding is that Tecplot was able to handle and visualize unstructured data grids long ago. Yes, yeah, absolutely.
All the data we've shown you and the data that we run, even the data that we test on, is unstructured. So.
Yeah. So yeah, we've been able to do that for a very long time. Yeah. What we're talking about today is we can load very large cases and visualize them. It's not just any unstructured grid.
Yeah. Two quick questions because we're running out of time here. One was around higher order elements. It's something that we've certainly, over the years considered putting in. It isn't going to be in the next release, but it's definitely on our backlog. It's probably worth leaving it at that at this point. In terms of the defaults, Yoram, you had asked about the defaults between the competitive defaults and our defaults. That goes back to that time to first image. In principle, Tecplot was going to show a surface. The time to first image for the tool that we tested against, in this case, just brought in the flow domain edge.
Yeah, just a box.
A box.
So, yeah. Min-max of the flow domain. Yeah. So those are very different, things. To get the min-max is pretty easy and create and draw a box.
Yeah.
And so we needed to come up, or apples to apples, so that it was actually generating an image.
There's a question about performance improvements 2011 to 2012. I think it's worth saying that, of course, we're always improving it, and it was depends on for what, but we did make some significant improvements both in slicing and stream traces.
Well, and the other big improvement we've made is if you're loading unsteady plot 3D, maybe this comes back to Yoram's question, but if you have unsteady plot 3D data, it'll be substantially faster.
Mm-hmm.
You know, I think in one case it was like a factor of 23 faster.
Wow.
Just because in the past we've had to scan through the data and now we don't. So we have made substantial improvements. Sometimes our improvements are focused in certain areas, sometimes they're general. And we did do some general improvements, especially when you have a lot of zones. Mm-hmm. It's substantially faster now.
And the last comment on that, if you're using a commercial code like Fluent, we've improved our Fluent loading performance very significantly because we actually have applied an indexing strategy for Fluent, and so that certainly helped. Mm-hmm. Someone was asking about, because a billion nodes is awesome, but I want to load 1 million second-order elements. Yeah, that's definitely post-processing programs. This is not an area where we spend a lot of time, but it's certainly an area of interest. The guys out at Lawrence Berkeley National Lab and the guys doing Tough 2, they'd like to use higher-order elements as well. So
yeah,
good question. We're just about running out of time. I wanted to thank everyone for your conversation and listening to what we had to say about large data. Our next webinar is a few weeks from now. We're going to focus specifically on Tecplot 360 2012 R1. And in that case, we'll actually go through some use cases in detail, highlighting some of the things that have changed. So if you haven't already signed up for that, you should see an email from me some point this week. And please join us. We'll be going through some of this in more detail. With that, that concludes today's discussion. Thank you again. And if your question wasn't answered, we will follow up with you directly. Thank you again, Scott, for sitting in this morning.
Thank you, Darrell.
And thank everyone for participating. See you in our next webinar.